Last week, introduced concepts like determinism, causation, freedom, um, in my overall survey of the topics that we will deal with during the course. So today that's the program today, to discuss the notion of determinism and causation or causality in the context of a concrete model of a physical world. And this is classical mechanics or Newtonian mechanics. And again, as I stated last week, and some people asked me, I already know physics, so what shall I learn? My point is not to give you a classical mechanics course, but to just highlight and discuss and elaborate the points which are related, are relevant to the conceptual notions of determinism and causality and related issues. All right, so before we start, I just want to, I put on the slide here on the top the Laplace demon, which I mentioned already, I discussed last week. And I must say Laplace was sloppy, because what he says, and I highlighted in bold, that this demon, this intelligent, super intelligent person, if it knows at certain moment or certain time all the forces and all positions of all items, then he can predict everything, past and future. This is not precise, even within classical Newtonian mechanics that Laplace was very well versed with. Actually, 50 years already before Laplace, there was already a statement about determinism, even more precise. And this is from Boscovich about 50 years earlier. And then he says that you have to know all positions and velocities of all points. And once you know that at a given time, then everything is become unique and determined. And this is more precise within classical mechanics. You have to know not only at a given time, not only the positions, but also the velocities of all atoms or all objects. Okay, so let's see why this is so. So on the left-hand side, you see kind of the basic, some of the basic laws of Newtonian mechanics. And I remind you, if you don't understand something, or maybe I have a mistake, just jump in and ask. If there is more conceptual discussion, we can leave it to time where I'll
just
for discussion.
Just a question.
Yeah.
So about Laplace, he wrote that you need to know all the positions, but also all the forces between the objects, right?
Yeah, but that's not enough. Yeah, of
right.
course.
You need to know the masses, but
no, but that's not enough. Even if you know all the forces, and we'll see here from Newtonian mechanics that that's not enough. Okay, so here's equation one, which is so imagine you have some number of particles. So I here, the subscript I is denoting the index of the particle. I didn't write here, but imagine I goes from 1 to n. N will be the number of particles. I imagine that we are talking about a closed and isolated system, so nothing influences the system. There's no interaction with the environment. Let's say this is the entire universe, for instance. Okay, so according to second law of Newton, the equations of motion that determine how the position of each atom or each object in the space in this system, xi is the momentarily position, the position of the particle at time t. So the way it evolves in time is by the second order differential equation, to the second derivative of xi with respect to time, which is the acceleration. And again, this is a vector, so it's acceleration in all three coordinates, x, y, and z, multiplied by a constant, which is the mass of the particle, which is constant, doesn't depend on time. And this equals to the Fi, the right-hand side, which is the force acting on the particle. Okay, this is basically the fundamental equation. So if you have 100 particles, so this is like 300 second-order differential equations. Okay, of course you have to know the forces, because otherwise you know what to put there on the right-hand side. Okay, actually it's easier to write it in a different fashion, is to split this equation into two first-order differential equations. In physics, we define equation 3, we define the momentum of the particle, which basically the velocity, essentially the velocity of the particle times the mass, mi times dxi dt. So this is pi, the momentum. And then the second order differential equation, equation 1, becomes now a first order differential equation about the change in time of the momentum. So equation 2 and 3 are equivalent to equation 1, but it's sometimes more convenient to write all the equations in terms of first order differential equations and not second order differential equations. So we have here the first order, the rate of change of momentum. I'm sorry, here mi should not be there. You see I have already a mistake. In equation 2, there shouldn't be mi, because mi appears in the definition of in equation 3. So dpi dt equals fi. The rate of change of momentum equals to the force, and the rate of change of x times mi equals to the momentum. And one of you students should be, every lecture should be in charge to write down all my mistakes so that I can then later on correct them. Okay, very good. So this is basically the basics of mechanics, of classical mechanics. Now, what else? This is the kind of kinematics. This is, if I know the forces, how the change, how x changes, or how x and p changes, but I have to know the forces. So part of the mechanics is to establish what are the forces. Okay, so here is, you all know gravity, apple falling from the tree, or planet's motion. I'll take something simple. Imagine that those charges, those particles have not only masses, but have also charges, electrical charges. So it's called electrostatic. And then Coulomb force, in this case, Fi, the force on the particle I, is proportional to the charge of the particle, Qi, and then sum of the contribution from each one of the other particles, sum of the J, and then it is proportional to Qj. The contribution from each one of the J's particle is proportional to the charge of the particle, Qj, and then inversely proportional to the distance between, square of the distance between them. So Rij square is the amplitude square of the distance between I and j, xi, xj. And then the direction, the contribution of each one of the particles to the direction of the force, because the force again is a three-dimensional vector, it is in the direction, in the unit vector of the displacement of the distance vector between xi and xj. I think most of you, maybe in high school, it's called the Coulomb law for electrostatics. It really defines, given the charges and their location in space, you can compute at any given time what will be the force acting on each one of those particles. Very simple. All right. I hope there is no question here. I think, except for my mistake, it should be clear to all of you. Okay. Now, suppose I put it back. I know the mi, I know the qi, and I want to solve these equations. So I'll have many solutions. Okay, so that's important. That's part of what we discussed today. And in order to get a unique solution, Okay, so here is an example before, yeah, in order to have a unique solution, you have to specify initial condition like any other ordinary differential equation. And in this case, because we have x and p, we need to specify at some time t, which I call it 0, but it doesn't mean 0. It doesn't mean the Big Bang time. It means just arbitrary, we call it initial condition. Then you specify all the positions of all the particles at that time, and you specify all the momenta, all the velocities of all the particles at this time. Once you do that, and you put it into the integration of those differential equations, you have a unique solution. Unique at all times, present and past. Okay, so how do we geometrically describe it? So it is tempting to write down something like maybe we do in high school. X in the y-axis, like in the right side of the slide, and t is the x-axis. So this is x of t is kind of how the particle position change in time. That's kind of the naive, intuitive way of describing how the solution looks like, but it's problematic because in this case, if x and t is plotted, x as a function of time, as a trajectory, then you have another solution that crosses it at some point. And so the problem is that these two trajectories in the xt plane may cross at a given time, and that's fine. So the reason being that although they equate their position x at this time is the same, they have different velocities and therefore they have different trajectories. So if we want to have a description of unique trajectories that don't cross each other, namely if they are equal at one point, then they are completely equal everywhere in time, then we are better off thinking about the notion of phase space. So phase space in physics is sometimes called in computation or in dynamics state space. It's the space of all possible states of the system. Now, a state in our case, in the mechanical case, if you have n particles, it will be 6n dimensional space. Why 6n? Because each particle contributes 3 coordinate in x and 3 coordinate in p. So altogether, each particle contributes 6 dimension. You have n particles, so this is 6n dimensional space. And that's called phase space. Every point, every vector, every point in this 6n dimensional space is a possible state of the system. Okay, so it's hard for me to draw 6-dimensional plots. So let's take the simplest case. A particle, one particle moving in one direction. It's basically the same as here, x as a function of t, but now the phase space will be 2-dimensional, will be momentum and position. So time here is not an axis, is implicit. Okay, so this is what you show here in this example of phase space. So for instance, if you look at the right-hand side, for instance, imagine this is like a sun or some object at the origin 0, which exerts a force on a planet, but this is not gravitational force because it will behave slightly differently, but it doesn't matter. An attractive force applying to the object, and then the object moves, and if it has sufficient momentum, in this case, it may move, accelerate towards this source of force, and then if it has enough momentum, it will pass it and go to the other side and decelerate because of the force. So this is what you see here in a plot, in a trajectory, which I denoted as 1. So again, x is the x and p is the y-axis, and every point here is a possible state of the system. So this is 2-dimensional phase space of a 1-dimensional particle that moves in 1 dimension. Okay, so you can see x in 1. Imagine that this is a planet that came to the solar system from minus infinity back there, and then it comes and approaches the origin zero, where the sun, our planet, our close to the sun, and it accelerates because of the pulling force, but then it passes it and goes to the other side of the universe. It decelerates. You see that the velocity goes down, but it keeps going and escapes the solar system, basically. Okay, so that's what the trajectory one means. So now I'm talking trajectory not as a function of time, but x and p, the chain of states that connected through the dynamics. Okay, so it's clear. So by the way, two is kind of a different, qualitatively different trajectory. Imagine now here that, like the Earth, it doesn't have enough initial momentum, so it basically circles around the sun, the source of force, attractive force. So it it accelerates, then decelerates, but doesn't escape, but goes around. So this would be a bounded periodic trajectory. Oh. So all kinds of solutions like that exist. All right, is this clear? Okay, good. So now it's clear that in the phase space, no two trajectories can intersect, because if the two meet at some point, it means that they have at this point the same x and p, and if they have the same x and p at this point, the solution is unique, so they must agree all the way, from minus infinity to plus infinity. Okay, the arrows that I put there is just to remind you that I'm talking about, I'm giving you a hint about the time, the direction of time. I'm going to insist from now, and I'll keep saying it. To me, when you write down differential equation like this in Newtonian mechanics, it's taken for granted that t is a variable denoting time, starting from minus infinity or some zero and goes to plus infinity. Time flows in the forward direction, period. You can read Hawking's and other cosmologists tell you about roping and time. Forget it. We are now talking about very clear. Time, for whatever reason, we can philosophize about it, starts from minus infinity or maybe from zero and goes in one direction forward. Okay, good. So there is another important aspect of, many important aspects of classical mechanics. One of them is conservation laws. There are many conservation laws, but I'll, for simplicity, talk about energy conservation. What does it mean? First of all, if you, okay, we'll see here. So in the mechanical system, the energy is at every state in the phase space, it has a given energy, and the energy is given by the sum of the potential energy V and kinetic energy T. In the case of electrostatic, the energy is the potential energy is given here. It doesn't matter. In the case of and the kinetic energy is the sum of the momenta square over m. What's important is that the potential energy is a function only of the state of the system. I'm sorry, of the coordinate x. And the kinetic energy is purely a function of the momentum. So what is the statement? So for every state x and p in the phase space, there is some energy. There is some value for h. It's the total sum of the potential and kinetic energy. And the statement is that this energy is constant. The value of the Hamiltonian is constant along the trajectory. Okay? How does it come about? So I won't go into derivation. There is a few lines, or maybe I'll do it quickly. If you don't follow, it's fine. I'm taking a derivative of h in time. So I'm using the chain law. H is a function of x and p, and therefore the time dependence comes through the dependence of x and p in time. So I take a derivative of the voltage the potential energy V with respect to x, because it depends only on x, and multiply by the velocity. I take a derivative of t with respect to momentum, because it functions only for momentum, and multiply by dB dt. Now, since we have to remember, I didn't say it, but the forces in this system is minus the gradient of the potential. Okay, so therefore, if we put it together, if you put it together, then you find that minus f times the x dt plus p over m times dp dt, you put everything together, you get exactly minus fi plus mi and times the acceleration, which according to the Newton's law, this is basically zero, so if everything is zero. So again, if you didn't follow it, it's fine. The only point which I want to make is that in mechanics, the conservation of energy and momentum and so on is basically is derived from the equations of motion. It's not something beyond it. It's a consequences of the equation of motion. Okay, so if I go back to my plot in the right-hand side, basically now I can, another way of thinking about the different trajectory is that the different trajectory have different energy. The energy in each trajectory will be the same, but for instance, this trajectory has a slightly different momentum, so it will have probably lower energy, this has lower energy, and so on and so forth. So you can index all the different trajectories by their energy level. Okay, conservation of energy. There's conservation momentum and angular momentum, but it's enough on this. Good. So now I want to talk about something which is very fundamental to many questions that are conceptual questions that are relevant to the course. And this is the property of micro-reversibility or temporal micro-reversibility. This is the property of this mechanical system that I described, okay? Again, I'm insisting on the fact that the forces will be only a function of x, not of velocity. Otherwise, there is no conservation of energy. But in the conservative system, in other words, system the way like the ones I described, there is a fantastic symmetry. And this is the following. Suppose I found a solution to the equations of motion. And I have now x of t and p of t as a solution, a trajectory in the phase space. Now, it's guaranteed that for each such a solution, there is another solution, x prime of t and p prime of t. That's another trajectory, another solution. But that solution is related to the previous solution, the original solution, by time inversion. So x prime of t is x of minus t. P prime of t has minus t in p, but has minus in front also. That's important. Why? Because what we do, we invert the sign of time. But when you invert the sign of time, the velocity itself is the rate of change of x. And therefore, the velocity has also to change sign. So you see here, I have p of minus t, but I have minus in front of it, not in front of x. Okay? This is something that, again, is a consequence of the equations of motion. It's very easy to prove. Maybe Ariel will put it as an exercise. As long as I said, as long as the forces are function only of the position and not the momentum, not the velocity. Now there is some confusion about this micro-reversibility, because often people talk about this other solution on the right-hand side as going from the future to the past. Okay, like a time machine. They say, in classical mechanics, you can go from the past to the future, you can go from the future to the past. That's confusing. It's either wrong or confusing. At least the way I established it, time always goes in one direction, not time machine. Always goes from minus infinity or from 0 to plus infinity or to something. Okay? In the right-hand side, it is the same. In other words, this is just another trajectory which goes from minus infinity to plus infinity. Okay? It's not a trajectory that goes backward in time. Okay, so let's see what I mean by that. Let's imagine going back to the trajectory 1. This is a possible solution. Okay? Now, micro-reversibility says, you know, that solution has another solution you can generate another solution by inverting time and inverting the sign of P. And what you get at 1 prime, the solution and the bottom. Okay? You can see why, because let's say the trajectory 1 started at x equal to minus infinity when time is minus infinity, and it comes to here at time 0, and then it goes to plus infinity in space at t equals plus infinity. Okay? So now we take this solution and say, what happens if I take plus infinity in time and invert the sign? So this will be minus infinity. So the new solution starts from plus infinity in space at early time, goes backward, the velocity now is changing in sign, so it decreases, and then escapes to the other side. Okay. So what I'm saying, both solutions are evolving in time in a forward direction. We are not talking about time machines. Both 1 and 1 prime are evolving as a function of time in the right direction, except that 1 starts in space at minus infinity and it ends up at plus infinity in space. In other words, starts on the left side and goes at time infinity to the right side. The other solution starts in the right side and evolves to the left side. But both of them are evolving in the forward direction in time. So it's not about time machines. Physicists, many just for practical reasons, and they use jargons and they say backward in time, particle propagate, but that's nonsense. Everything propagates in the right direction. I think it's something that you should internalize, that otherwise you don't know what we mean when you talk about time. Okay, is it clear? Okay, so people, you know, you take a movie and people show you, I don't know, Charlie Chaplin going backward. No, it's not. It's not just taking, you know, somebody moving in the forward, but just now stepping backward. You know, like you run it. You take, the person has to turn around and go backward. Good. Okay, micro-reversibility. So once we understand what does it mean micro-reversibility, now I open it to a discussion about the relation between what I said until now, principle of causality and Newtonian mechanics. But before that, if there are questions, please stop here. Stop me here. If you understand my schemes, you know. Yes.
אני מבינה שיש פתרון מתמטי שיהיה סימטרי להחלפה בזמן.
מי שואל?
עדן.
מי שואל שיצביע?
עדן. אני אומרת, אני מבינה שיש פתרון מתמטי לסימטריה בזמן, אבל אני לא מבינה האם הוא גם פתרון פיזיקלי.
קודם כל אני לא רואה אותך. איפה עדן? אוקיי, את שאלת. תחזרי על השאלה.
אני אומרת שאני מבינה שיש תמיד פתרון מתמטי סימטרי להחלפה בזמן, אבל מה המשמעות הפיזיקלית של זה? והאם זה פתרון פיזיקלי?
כן. Okay, so Eden asked, she understands that mathematically this is the way it goes, but is there a physical, is it a physical meaningful solution or symmetry. And I think it's very physical because the way I explained it, you see, imagine some meteor starting from the right-hand side of the universe, whatever it means, and then approaches the solar system, and then escapes to the left-hand, starts from the left-hand side and escapes to the right-hand side. That's a trajectory, right? A solution. Now, what the microreversibility says is that there is equally possible condition, a state or solution, which is backward, which is a particle or meteor starting from the right-hand side of the solar system, approaches the solar system, and escapes to the left-hand side. Why not? These two equally valid scenarios. There is nothing special about starting from the left-hand side and going to the right-hand side of the source of force versus the opposite, starting from the left-hand side and escaping to the right-hand side of the source of force. I think it's perfectly makes sense physically. The mathematics is guaranteeing it, that you don't have to say, well, maybe there is something. No, the mathematics guarantees, but it's very intuitive physically. Once you don't think about time going from future to the past, then the way I described it, I think it's very physical, very plausible, right? There is no reason why one solution would be possible, not the other. Right?
Can I also ask a question?
Yes.
So I understand what you said about the one object coming from the right and the other one coming from the left. I can't understand why we write that as minus t. Like,
okay. So let's assume that t equal to 0. Let's look at the trajectory 1. Okay. So let's say 0 is when it is an x equal to 0 in the middle. Time equal to 0 will be here. Okay, will be here. Okay. So let's imagine that at t equals minus infinity, the particle at 1 was at minus infinity, was at the left-hand side minus infinity. Okay. It moves. It comes to the origin at time t equals 0, and then goes to the plus infinity in space at time equals, I don't know, plus infinity, okay? Now I'm saying the other one, the other solution, I'm giving it its initial condition, let's say at minus infinity. Where the other solution, where the other particle will start? It will start at t equals minus infinity, but at which space? Well, it will start at the same x as the other particle was at plus infinity, because I take x and I invert the sign. So 1 prime will start at t equals minus infinity at the same position as the particle of 1 started at was at plus infinity. This is the change in time, right? So x at minus infinity is the same as this guy was at plus infinity.
mm-hmm.
Right? I take x at plus infinity, I invert the sign. This will tell me where this particle was at minus infinity.
Okay.
Okay, so it means that I take particle 1 at time, I take its location at time equals plus infinity, somewhere here, and this will determine the location of the new particle at time minus infinity, because I change the change in time, the sign of time. So now the new particle will start at x equal to minus infinity, to plus, at x equal here, because I change the sign of time. Where the other particle ends, this is where this particle starts, because I change the sign of time. Okay? This is about x. This is about position. Now I can ask myself, what is the starting velocity or momentum of the new particle? Well, I do the same. I take the velocity of the particle at, let's say here, which is a positive value because it's above It's above it's an upper plane at plus infinity, and I say change the sign, so going from positive to negative, and this will be now the momentum of the new particle at minus infinity, right? Because in P, I change both the time, the sign time, and the sign of velocity. So now I know what the new particle does. It starts here, the same as the other particle ends. This particle will start, but it will start with the opposite velocity that this particle was here. So this is why it will start from here and move in the other direction. It will move towards the origin rather than from the origin. So it will move from here towards minus infinity in space. Okay. You see, it's very intuitive. You cannot, if the particle starts, if you want the symmetry, you have to allow, you must enforce the velocity to going backward, because the velocity is the rate of change in x. But if you want x to go in the other direction, then you have to change the sign of the velocity. So this solution takes the same final value of x of that solution as its initial value, because of the change in the sign of time, and it takes the velocity of this, the end velocity of this trajectory as the initial velocity of this guy, but with a different sign. This is why it goes from plus to minus. This is why it is in the lower, but it's in the bottom of the plot, which is negative p, rather than the upper plot, which is positive p. And therefore, you get a trajectory which begins here at this x and has negative velocity, so the x is decreasing, so it's moving in this direction, because it is in this position, but now with a negative velocity. So the position x decreases with time, and therefore it moves from right to left, whereas this guy moves from left to right. Okay?
Thank you, yeah.
Okay. We'll have hopefully some more exercises, more examples of a pendulum and so on and so forth in the homework assignment, so you can think more about it and see that it makes perfect sense. It maybe the formalism looks weird, but it makes perfect sense. But to me, the important thing is to understand 1 and 1 prime, both of them describe particles that start from some place in space with some velocity at time, at whatever, some time, and moves forward in time. Both of them, they reverse direction in space, but they move forward in time. We're not thinking about reversing time. In other words, that we're not thinking about solutions that go from future to past. It doesn't make sense. Good?
Well, you're basically saying that if we have a solution for one problem with x of t and p of t, we can deduce from that a solution for a different problem because it has a different initial condition. Maybe that's what's confusing. It's not the same.
Absolutely. Absolutely.
It's different.
Absolutely. The initial condition, the final conditions are now reversed. Absolutely. It's a different trajectory. Exactly. It's not, if it's different trajectory, it means it has different initial condition. By the way, because of the symmetry, you can convince yourself that it has the same energy level. But the momentum is reversed. Absolutely right. It is the same equations of motion. In this, it will have the same energies, the two trajectories, but definitely because there are two trajectories, not one, then they have different initial conditions. The final point in one is the initial point in the other. By the way, trajectory 2, let me ask you, what will be 2 prime?
Same thing, just Reverse
What?
it's the same thing. You can reverse the arrow, but it's meaningless because it's a closed.
Exactly. So exactly. Periodic orbit 2 and 2 prime are basically the same trajectory, right? Because it doesn't matter. You start here, you end here, then you start here, you end here, then you go back to here. So in this case, 2 equals 2 prime. Okay. I'm not reversing the arrow. You see, it's the same thing because time goes in one direction. So it's the same. 2 will be equal to 2 prime in this case. Periodic orbits will be the same. Okay. Good. So let me suggest before I go on to discuss causality and so on, shall we make a break here or shall I continue?
Yeah, maybe we should have some break.
Okay, so 10 minutes break. What to Ariel?
10 minutes sounds reasonable. Yeah.
Okay.
So we'll be
Let's
back
try
here at
4:55. Let's try to everybody be back. 4:55. I'm around. If somebody wants to ask me a question, it's fine, but הפסקה. All right. Okay. Okay, I want to, before I go on, I had a question. I want to, just to alert all of you, maybe some of you also misunderstood my notation here. When I had X prime and P prime, it didn't mean a derivative. I'm sorry for that poor notation. It meant just a symbol of, and that's I wanted, that's a notation of another trajectory, like 1 and 1 prime here. It's not a derivative. Sorry for that misunderstanding. Okay, so, all right. Okay, so this is all the physics that you need, more or less. And now let's discuss the consequences or the conceptual consequences. Okay, one way to, I want to put up front, to put a puzzle that every one of us must be struggling with it at some point. And this is why I could in the morning today sit and prepare my lecture for the evening, for the afternoon, but I couldn't prepare the lecture for last week. I couldn't prepare today the lecture that I gave last week. Now it sounds weird. How can you do something now that will affect the past? Now, of course, it's impossible. But why it's impossible? Why the past is sort of immune from our present actions, not the future. So we can act on the future, on the other hand, and memorize the past. What is the origin of this asymmetry? Turns out there is no simple, you can give simple answers, but once you elaborate on them, you see that it's not easy to defend those simple answers. But this is basically the question. What is the origin of the fundamental difference between the relation of the past to the present and the relation of the future to the present? Okay. It's so weird a question that we don't even know whether the answer is logic, that it's simply illogical to talk about something affecting the past, or it is philosophy, metaphysical, God creates the world in some sense, in this way, some metaphysical answer, or it is physics. Maybe physics says that you cannot do that. You can influence the future, but not the past. So we want to see if physics can explain that. Okay. So this is related to the principle of causality or causation, causality in physics, in classical mechanics. So I'm giving you in the slide a famous quote from Erwin Schrödinger, the founder of quantum mechanics, but he wrote on many other things. And he says, what is principle of causality? He says that if there is something happening at some position, point P is position here, not moment, at some point in space, at some time T, then this is determined by whatever happened in some neighborhood of P at some time T minus tau before. And that is the cause, the event, the situation in the world, in the neighborhood, spatial neighborhood of P at some previous time T minus tau, that determined what happens at time T in the position P. Okay, so basically it's very intuitive and it has three elements, this statement of causality. First of all, determinism, you know, events in one time determines what happens in another time. It has temporal asymmetry. It says relation of causality must be that the cause comes before the effect. So there is the causality is working along forward in time. And then it has the locality in space and time. In other words, what happens now here is caused by what happens in the neighborhood of here, some previous time T minus tau, in some delayed fashion. So it's spatial temporal locality. So these are principles, these are elements of what we would like to have in a notion of causation or causality. All right. So we have determinism. Let's see if we have the other things, okay? So, but this is a starting point for a discussion about all these elements. Okay, so let's talk about determinism. On the one hand side, it sounds very intuitive that you need that something that determines what happens, A determines B, but some people argue that determinism, by its own definition, even without micro-reversibility, any system that is deterministic, any set of systems that obeys differential equation and so on, and you have trajectories and so on, it, by its very nature, doesn't obey causality in the sense of that the present affects the future, the temporal asymmetry. And why is it so? So let's take an example. On the left-hand side, I'm giving you a set of equations, equation 11, which is an example, a deterministic set of equations. You know, you can solve it. The same as what I said before. You have X, you have P, you have second order. It is the same Newtonian equation, except that there is friction, there is a viscosity, there's viscous force, and the viscous force is minus gamma I times dx dt, is proportional to the velocity. As you all know, the faster an object slides, the stronger is the friction. That tries to stop it. So this is this minus gamma I dx I dt. So that's not conservative system, because the energy dissipates, is decreasing as the particle moves to heat to the environment. Okay, so, but it's deterministic. It's, you know, it's well defined, second order differential equation. In order to have a unique solution, you need to find X and P at a given time, and then you know everything, past and future. Okay, so here is the phase space example of such a system, again, one particle in one dimension, x and p, as before. And here is an example of trajectories, okay? Again, trajectories don't intersect, except for the origin where they kind of at time infinity, all of them go to the origin. But what happens is the particle starts, in this case, starts at the, it's the same as, you know, a planet, but now it's not in the space, but there is two, you know, in water or something that it dissipates heat. So it's the particle, sorry, the particles, let's say, start here and, you know, losing momentum and then doesn't go the other side of the universe, but is being trapped and not even oscillate periodically, but essentially going, it stops. It's going to the minimum of the potential because it loses energy. The kinetic energy it had, it just, the total energy dissipates and goes to the minimum. Okay, so this is typical. You have, you know, variety of these trajectories. What is funny here that they all, at time goes to infinity, all of them will go to the minimum of the potential and stop there. So this is what's called stable fixed point, okay? You don't have it in Newtonian mechanics because either they escape or they go around. Unless they start from the origin, they'll stay in the origin, but otherwise they'll do the trajectory that I showed you, this kind of trajectories, okay? Because energy is conserved. Here, energy is not conserved, and it goes to the minimum value of the energy, which is basically here. Zero momentum and minimum of the potential. All right, good. So now you can see, so there is no micro-reversibility here, right? Because in this system, for instance, if I start near the origin, I will never go in the other direction and escape. No way, right? Because the energy will just dissipate. So I must go here. So there is no micro-reversibility. You can see from the nature of the trajectories, okay? However, still it is true. I take a trajectory here, and I pick two states, A and B, okay? And I'm asking, here the table on the right-hand side, I'm asking which one is causing which one. So you can say A is causing B. You know, if I know initial condition A, then I can calculate and know B. But at the same time, I can also say that if I know B, then I know what A is. Okay, so that's the argument that once it's a deterministic system, it doesn't matter energy conservation, micro-reversibility, by the very fact that it's deterministic system, once you have in the phase space, once you have a point in the phase space, it determines uniquely the trajectory both in the past and in the future, like Laplace said, like others said. So what is causality here? So that's kind of the argument of causality from determinism. Because it's a point determines both the future and the past, then in what sense you can say A caused B rather than B caused A?
This is true also for,
yeah? Go
this
ahead.
is also true. This is true for a conservative system as well. You're saying even if the system is dissipative, right?
Even if the system?
Even if there is friction and the system is not reversible. I mean, you gave a different example now, but the argument
what I'm saying is that the micro-reversibility will add another subtlety, will add another complaint. I want to disentangle the two complaints.
You're saying even without reversibility.
What?
Okay.
Yeah, what I'm saying is forget about micro-reversibility. Here is a system that does not obey micro-reversibility, but is deterministic. By the very fact that it's deterministic, you can say, once I know the state of the system at time, let's call it 0, I know the state of the system in the past as in the future. It's exactly like Laplace said, but even without micro-reversibility, this is true. Okay, so in what sense I can say the state now caused the future state, but not caused the previous state? Now, you can argue that's a valid philosophical or conceptual question. I think in this case, I think I can argue that there is difference. because the very fact that energy decreases, it gives some special error. It gives some special sense, physical sense to the direction of time. I can say to me that being in a state A with high energy and given the forces which are dissipating energy because there is viscosity, then this explains why I end up being in near the origin, because the energy decreases. It's not the same, it doesn't have the same explanatory force to say, well, I am in the origin and therefore I was in A in the past, because there is a well-defined physical process which explains why you go from high energy to low energy. It does not explain why you go from low energy to mechanistically to energy. So what I want to say is that you have to disentangle determination, in other words, the ability to compute, to determine, to predict in a theoretical sense, the state of the system. This, if the system is deterministic, then there is no difference between future and the past. Once you know the state of the system at some time, like Laplace said, then you know the future and you know the past. But I think causality is more than that, is something that brings about, that produces it explains in a physical sense why you go from A to B. And I think that type of explanation is more natural in this case to explain why you go from A to B, rather than to say that why you go from B, you started in A. Okay, you can argue against it. I'm just giving it as a thought that once you have a well-defined physical process that has error of time, then I think that determines the causality explanation, or can determine the causality explanation. That's in my view. Okay. Now I want to go to our system, because many complain about micro-reversibility. They say, okay, that's very nice. You can argue about it here. But once you have micro-reversibility, it's not like here that in the future, there is well-defined sense that the future, everything is here. It looks very different from the past. But here, it doesn't look like that. I mean, the future, the past looks the same. So you have now micro-reversibility, okay? So micro-reversibility, again, I want to, again, disentangle it. People say, again, why because of micro-reversibility, then I can go, again, people say in the jargon, sorry, because of micro-reversibility, if I go from A to B, then at the same time, I can also go from B to A. That's wrong, but you can find it in the literature. The way I specified it, and we are looking at the phase space of the system, micro-reversibility doesn't say that you go from A to B and you can also go from B to A. In this case, at least, you see micro-reversibility says that if you go from A to B, then you go from B prime to A prime because of micro-reversibility. So this is something that, in my view, doesn't violate causality, because I can explain, remember my meteor, I can explain in trajectory 1 why the system goes from A to B. It starts from positive velocity and accelerates and go to the other direction. So A, in some sense, with the forces, the fact that it starts with a positive velocity and knowing the forces explains why it got to B later on. And I can easily explain why in 1 prime, starting from B prime, which is in the same position, but in opposite velocity, you end up in A prime. So I think both have very valid causal explanation. So I don't think there is any problem here because of the way I see the table, right? Call A, XA, PA, B, XP, BP, but now A prime, the other one has minus BP. Okay, so it makes sense. It makes sense. It makes sense that A causes B and B prime causes A prime. There is no problem. in my view, it is consistent with the notion of causality, despite the fact that there is micro-reversibility. Okay, so here is an example of that, a mechanical example. Now I'm plotting here, not the phase space. Like I had a question from Shai Yelnik. I'm plotting now two particles that move in one direction. So one of them, two particles in one-dimensional world, particle A and particle B. One trajectory, the blue trajectory, is particle A starts from with some momentum, doesn't show here, starts from some position here with a velocity, and particle B, the ball B, the billiard ball B, is at the origin, at rest. So A kicks B, B moves in, again, in the X direction, and A stays here. So the initial value in the state A, in state A, particle 1 was at X1, particle 2 was at the origin. This is state A, but because of the velocity, it ended up with state B, where particle 1 is at 0, and particle 2 is at X, whatever X is, okay? Now I do the micro-reversible trajectory. So what it will be that the particle that got kicked and has now velocity in the positive direction, now I'm taking it at the same position, but reversing the velocity. And particle A, I'm taking its initial value to be now the final value, to be what it was the final value. So the story is very simple. In one trajectory, B here and A kicks it and B moved. In another solution, B has a velocity in the negative direction, so it comes to the origin, kicks A, and A move. Both of them are time reversed of each other, but I argue that both of them have very plausible causal story without any contradiction, because the velocity changed, okay? So it's very easy to explain why in one case you go from state A to B, and in another case you go from state B prime to A prime. Okay, what else remained to be explained? Anybody can guess? Okay, I'm here.
Maybe
okay.
maybe the bound state of
The bound state, very good. Now now let's look at the periodic state. Now it's more challenging, right? Because now it's not 1 and 1 prime and there is no something, right? So imagine now I take two states, A and the future state B. Well, so I would say A causing B. But later on, B will evolve into A. So now I have A goes to B and B goes to A. So you can ask what's going on. Either A causes B or B causes A. This is more subtle, and I don't want to argue one way or another, but in my view, both of them are valid. Again, there is no problem. A caused B because we know the forces, we know and so on. And state B, when there are forces, that brings about the evolution in time to A because it's periodic. So in my view, even that is not a problem. It's not against our intuitive notion of causality. That's what I want to say. Okay.
Can I ask a question?
Yes.
I think I understand the arguments, but I'm not quite sure what are we arguing against. I mean, who would suggest this is not causality?
People have a notion that if A causes B, there is something distinct in A, in the cause, which makes it causing B, and you cannot reverse it, right? That's the notion. I turn on fire, and the house is destroyed, is burned down. So igniting a fire is the cause. The house burning down is the effect. Now, you cannot say that, you know, the house burning down will also at the same time be a cause of my igniting the fire, right? So in our intuition, looks like A as a cause and B as an effect, there is something inherently different, asymmetric between them.
I would argue that this is the error of time.
So
Because we define effect.
do you imagine that there will be some scenario in some world where if I burn down my house at a later time, there will be igniting of fire, ignition of fire?
No.
No, but here it is. A, imagine A is my ignition of the fire, my setting the fire, and B is my burning the house. The house is burned. But here, the house in burned is evolves in time back to A.
But a fire in a burning house wouldn't look like this on a phase plot.
Why not? Why not? What's the difference?
The energy is not conserved for once.
Okay, so so we're starting. Okay, so we are starting to. We're starting to argue about it. Okay, so people might say, you know, that in this case, in the periodic case or in the micro-reversible case, there is no notion of causality. There is just trajectories, and that's all. You cannot say that A caused B and B causes A, but both of them are not causing anything. They're just part of the trajectory. That's the argument, whether it makes sense or not. I don't want to elaborate too much on it. It's, you know, already I mentioned my last week that Bertrand Russell, because of this and other similar argument or other arguments, says, forget about causality, forget about causation. It's not part of our world. It's just confusing. Talk about trajectories, that's all. Talk about state and trajectory. There is nothing causes anything else.
I have a misunderstanding.
If our notion, intuitive notion that something happens because something else caused it in the past is consistent or is coming out of physics. So you're saying, okay, well, my example is not good. So basically you are saying, let's go back to this. You know, you can say this is the burning of the house and this is the ignition of the fire, and now it cannot go in the other direction. That's good. So you basically say that our notion of causality holds for non-conservative system, but does not hold for conservative system. That's the answer. That's possible answer. I want to save it. I want to say even in conservative system, I can say that A caused B, and I don't have any problem with saying that B also causes A. That's my argument, but I don't want to defend it too strongly. I'm just saying, you know, people, physicists or, I don't know, philosophers, they argue about this question, whether in a system with micro-reversibility, you can actually meaningful talk about causality, causation. Okay.
Haim, can I ask a question?
Yeah. Yes.
Thank you. So I just want to make sure I understand. So is the claim here that the notion of causality, but basically what I'm asking is what defines causality in your opinion? Asymmetry is not part of it, because we see here a case where there is symmetry and you still claim that that would be causation or not? Or like, no. Are you going with the definition of Schrodinger?
No, I basically what I'm saying the following. Causality requires the temporal asymmetry. And I'm not claiming that I can derive this asymmetric notion of causality from the physics of micro-reversible system. But what I'm saying is that causality, the notion of causality, is consistent with that.
With the temporal asymmetry.
With the temporal symmetry of with the micro-reversibility. Okay. In other words, what I'm saying is causality is asymmetric notion. Okay? But if I look now at this periodic orbit, I can still say A evolves in time because of the forces and its initial value. If I start from here, I evolve in time in B. So I can say A and the forces caused B to happen. And it doesn't, and at the same time, I can say that if I start from B and the forces, then it will evolve into A.
Because there is still the
What
temporal
I'm saying,
asymmetry.
these two
Because time is,
statements,
okay, I understand.
exactly.
Okay.
I'm not claiming that B in this, I'm not claiming that here, go back. I'm not claiming that B here caused A. Causality is forward in time. But I'm saying I don't have any problem. It's not a contradiction to say that A is causing the future production of B and B is causing the future production of A.
But this is not the issue. Can I'm 100% fine with the explanation with microreversibility in the unbound state. Yeah. But if you have, right, because even though there's a reversibility, you have to take a different trajectory with a different P. But in the case of the bound state, assume that something started in a bound state at time minus infinity. I don't know if it's possible. Maybe that's where the answer should lie. But if something existed always in a bound state, then the fact that it was in A at Sunday and then it was at B on Monday, and we say that A had some effect on B and not vice versa. And you say, I agree that A could cause B and B could cause A at a future time. But in the phase space, without referring to the arrow of time, just the states, how could you talk about A being the past cause of B and not B being the cause of that same A, not the A that would be in the future when we go into that part of the system again? If I have something orbiting the sun and it was on a certain point on Sunday, then it's a different point on Monday, I don't care that it would go to that point in the future. The question is about...
For the same reason, I wouldn't say here that B caused A.
Because then you have to go through a different momentum, different states in the phase space.
Okay, that's fine. I mean, I don't want to defend it too strongly. That's my own feeling, but it's maybe weak. That's fine. It's just a question of what do you demand of causality, but it's a weak sense. I'm just saying it's consistent. Right. You may say,
well, if you relax your demands, if you relax the demands that you listed in Schrödinger's.
Okay, that's fine. I'm just want to say that even in the periodic, when I say B causing A, I don't mean going backward. I mean B as initial condition will cause A in the future. But again, it's a weak point. Okay, it's fine. It's not too strong. I can argue back and forth. Okay. Okay, there is another notion, very popular notion of causality, which says the following. Let's not talk about the entire world. And let's not talk any closed system that we are part of that system. Because if it's deterministic, then especially if it is microreversibility, as you argued, Isaac, A, because, A and B are two states. I mean, the fact that you are in the future, it doesn't matter. It doesn't mean much, okay?
Can I ask a question?
Yeah.
And theoretically, will you say that the universe, the entirety of the universe is a closed system?
Oh, I would say so.
You think so?
I think so.
So if it's so, like, then microreversibility is possible. If the entire universe is a closed system,
that's a very good question. We'll devote a special lecture or 2 lectures on that later on. That's a very good question. Okay, but let's.
You're arguing against it right now, so.
No. Okay, let's discuss it. Let's leave it to when we talk about thermodynamics. Precisely this question. Okay. Okay, but another notion of causality is that it's a notion of perturbation. So let me give you here. It says the following. Imagine that it's not the universe. We have a system that evolved. So now this is X and P, I forgot to say, X and P. And here is a trajectory of the system. And imagine that at a given time, I manipulate, I apply a perturbation. I give it a kick, I give it a force. So now the system at some point, at some time is perturbed, okay? And now the statement is, no, look, what will happen? Will happen is that without the perturbation, this will be the state, A and then B going here. And let's imagine at some time T perturbed, I do perturbation, I do apply a kick to the system. So now the trajectory will be different. So at time T, it will be in B prime, not in B. So it is legitimate to say that A is causing B in the sense that if I change A by a perturbation, I'll get a different B, B prime. Okay? That's the argument. Well, sounds interesting argument. Now I claim even this argument has a problem. Here is a problem. What is the initial condition that we imagine in this scenario? Okay, here is one scenario. Initial condition that fixed the trajectory, this trajectory, the first trajectory, the unperturbed trajectory, the blue trajectory is the unperturbed. Imagine that I start here in T initial, some T equal to 0 minus infinity. I fix the initial condition, and that fixed the trajectory, the blue trajectory, the unperturbed. Now I say, let's imagine I perturb at time T perturbed. Well, when I perturb, I have to decide whether I change the initial condition or not. No, but no, okay? So the initial condition is still the same. Well, in this case, indeed, this part of the trajectory will be the same because T initial is the same. The trajectory is unique. Up to now, the two evolved in the same equation. So the two trajectories will be identical in the past and will change in the future. Okay, but what happens in this case? Imagine that my initial condition is here, is in a later point in time. Well, now it's opposite. If I am perturbing the system here, well, this part is the same. The only thing which will be different is the past. So now you can say that A determined the previous state B because it changed B and B prime. Okay, you see where things are subtle. Okay, when you hear this story, it makes so much sense because implicitly you assume that the initial condition is in the past and you cannot do anything about it.
Maybe we can use the same definition recursively. What? Meaning don't use the definition recursively. Don't stop at A, but go all the way back to T initial. When you talk about T initial, every time step has to be defined in relation to other states of the system because it could have caused it had we perturbed it then.
If you start from the initial condition, the Big Bang, and you have a trajectory which unfolds, and you are saying, if I perturb the Big Bang, then the trajectory will be different, then I agree. Then the initial condition, if you change it in the past, it will change in the future. That's fine. But at the same time, you can say, suppose I define the fate of the universe in T equals to infinity or some T equals to 20 billion years. This is, I define that as my initial condition. Then I perturb the final state of the universe. I change the history of the universe. Which one is more legitimate than the other? Okay, so it's not simple. That's what I'm saying. I'm saying that the idea that causality is control. You know, A causes B because when you change A, you change B. That does not by itself explain why the causal relation will necessarily go in one direction and not the other, unless you add to it an implicit assumption that the initial condition was in the past. That's all what I'm saying. You can think about it, you can argue about it, just give you some thought about it. Okay, let's move on. There's another notion that remember that Schrödinger said, locality, that things in a position in space at a given time are affected by the neighborhood of that point at some delayed time, previous time, t minus tau. And the question is now whether Newtonian mechanics agree with that or not. Well, so first of all, it's well known that Newtonian mechanics is has the weird feature that a force Fi, a force at a given time, is instantaneously affecting the acceleration of the particle I, even if Fi is generated by particles very far away. Newton was very upset about it. This is what's called action from distance, or instantaneous or spooky action from distance. And Newton thought this is a very basic flaw of Newtonian mechanics, okay? The fact that there is this instantaneous action, that a particle far away exerts instantaneously a force on the particle in the origin. Okay, so in that sense, locality in time is violated by Newtonian mechanics. And in the lecture next week, we will see how in modern physics, beyond Newtonian mechanics, this is relieved, this is solved. Okay. However, I want to add that there is a sense of spatial locality even in Newtonian mechanics, because if you remember, the forces in F, for instance, in the electrostatic and in gravity, has this distance dependent. So although it's true that they act instantaneously, but the strength of the force falls in time. So in that sense, there is a spatial local nature to Newtonian mechanics, in that sense that the further away you are from a particle, the less effect you have on it. So that's something which is important, even within Newtonian mechanics. And in our day-to-day physics and biology, when we'll talk about this aspect of locality and so on, that's something that we will have in mind, because special relativity is something with velocities close to velocity of light and so on. It is important in principle, but it's nothing to do for our day-to-day experience or energy and scales that we are dealing with in biology or in day-to-day engineering problems and so on. Nevertheless, the locality in space is always there. Things we are near each other have much stronger effect on each other than if they are far away from each other. And finally, I want to add two more comments. One is what I call linearity. There is, or additivity, there is another aspect of, which you can call it locality, but anyway, of Newtonian mechanics, which I think it is fundamental, and that will go through all our discussion up to the end when you talk about free will and whatever, is the fact that the forces, suppose I have now a sphere full of charges, and I am in some point inside or outside, doesn't matter. And I want to compute the force that this collection of charges, distribution of charges act on me. And the answer is, it is simply a sum, a linear sum, addition of the infinitesimal contribution from each one of the tiny charges that makes this sphere, okay? This is something you can ask yourself, must be so? What is the reason that the laws of nature has these properties or not? We'll come to it. It's a very important feature. You can think about it as coming from locality in some sense, and we'll discuss it later on. But that's something, electrostatics is like that, gravity is like that, and so on. The net force is sum. It's simply additive contribution from individual. And it's extremely important, because when you talk about the relation between macro and micro, we will be faced with that whatever the macroscopic system is and complex is, at the end, the way it affects some molecule anywhere, it is by the contribution of all the atoms in this macroscopic thing. Okay, we'll come to it. Very important, in my view, very important notion of locality. And then I want to add just another comment, which is sometimes confusing. People, when you read, particularly philosophers, but of science, I mean, maybe others say, well, it's not true that physics is local. Why? Because there is a conservation law. So it is true, as you see here, that the forces fall off with distance, special relativity, things will have time to propagate. But what about conservation law? The energy has to be conserved. So if at some point there is a change in the local energy, it must be compensated by some other point. But conservation of energy is a property of the total closed system. So it is a global notion. And some people interpret it as an aspect of physics which is not local, because it's a property of the global system. And I think it's a mistake, because if you go back to my beginning of my lecture, I showed you very rapidly that conservation of energy is just derived from the law, the local, so to speak, laws, especially local laws of the it's not an additional global feature of the theory. So in other words, what I'm saying is the following. Whenever you have an argument about conservation energy and somebody says, well, if this particle here changes its energy, then another particle there must change its energy to compensate and to get conservation law. It is true, but if you ask how it happens that this particle knows about this particle, and the answer is no. It goes through the forces, it goes through the equations of motion. It doesn't happen in some, well, now I have to conserve energy, I don't have a choice, I have to change myself. Conservation of energy is mediated by the same dynamic processes of the equations of motion that I described before. Okay, so let's just summarize. In my view, the principle of causation, in my view, is consistent with, first of all, being a deterministic system. And it's consistent even with micro-reversibility, although you can argue against me, that's fine. That's my own intuition. But I agree, some parts of it are weak. But even that, I want to say, what I'm claiming, it's consistent. I'm not saying that I can derive the causal principle from Newtonian mechanics. I just say, if I insist on A at now, causing B in the future, if I insist on that, it is not violated by the micro-reversibility deterministic dynamic. There is action from distance, we discussed now, and there is a role of initial condition in the way, in my example, which is important because often the arguments about causality assume implicitly something about the initial condition in the past, not in the future, and we'll come to it. The initial condition story will haunt us in many lectures. Okay, you will see it. I want to add something which is the following. You can say, okay, so who wants causality? Just solve the equations and that's it, and find the solution. Forget about causality. I think that causality, the intuition of the principle of causation is a very useful guide to not to err, not to make mistakes when you do science, when you do even physics. Okay, so for instance, in the homework assignment, you will have an example of a simple gravity system with a weird geometry where the system allows several solutions. One solution is kind of intuitive. The other family of solutions is kind of crazy, pathological. But it's legitimate. It's part of the equation. It's a legitimate solution of the equation. And I would argue that if you keep the intuition of causality, you will see why that pathological solutions, forget about them, because they violate the sense of causality. Now you can say, okay, but who are you to disregard solutions which mathematically are legitimate? I would say no, but it means that if you go to some deeper microscopic physics, you will find a way to do. And the same will happen next week. I'll devote part of my lecture next week showing you a very nice example in electromagnetism of equations that have two families of solution. One seems to obey causality, another one seems to violate causality, and we know the one with violate causality, forget about it. We just ignore it. And we will ask ourselves, okay, fine, why we ignore it? Is there a deeper reason? But I would say, what I want to leave you with, I think the intuition of causality, whatever its metaphysical origin, holds in all physics, including my view, including micro-reversible Newton mechanics. And it's important to get hold of it, not to give it up, because otherwise you get very weird results and pathological results, which are nonsense. Okay, this is it.
Can I just rephrase if I understood correctly? The problem of Newton with Newtonian physics was, if I have, for example, a heavy mass approaching a second heavy mass in a very, very fast manner, then the second mass basically feels the first mass immediately, even though if the first mass would approach the second mass with the speed of light.
Are you referring to the action from distance?
Yes.
So, yes, but in that case, the problem is not so severe because the interaction between the impact is when they are very close to each other.
Okay, obviously because of the distance, but the problem is that, I mean, even if the one mass approaches the other mass very fast, like the gravity forces of the second mass feel the first mass from the beginning of the motion and until the end, even though we can assume for the toy example, the first mass approaches the second mass with the speed of light, so there's no information transfer possible between the two objects.
Yeah, yes, but you can equally say the following. Suppose I turn on I have a planet, okay, whatever, an object in space, and I turn on, so to speak, the sun. I put a sun in some point in some point in space. Immediately, as I put the sun there, immediately that object far away changes its acceleration. You see what I mean? There is no delay. As soon as you put a mass in the origin, at the same time, you have a force out there. And the acceleration is changing immediately, instantaneously. So that's what means instantaneous action from distance. What you would like to have is the following. If I put a sun at some point, time t in the middle, then after some delay, depending on the distance, that planet will feel it, okay?
Yes, exactly.
But the fact that the change in acceleration is instantaneous with the presence of the force someplace else, instantaneous, that's what means action in distance. The physical changes happen across distance simultaneously in time, instantaneously in time. Imagine you don't have to,
No, I understand.
You don't have to turn on the sun. You can take the sun and change slightly its position at time t. Okay? The planet Earth will change its acceleration instantaneously. If something happened to the sun, planet Earth in Newtonian mechanics changes its acceleration instantaneously, right? It will not jump, its acceleration, it's second order. So it will change the velocity and so on. So the trajectory will be smooth because it's a discontinuity or change in the second order. But still, it's an acceleration, it's a force. The planet Earth will feel the force or change in the force pulling it to the sun if I make a change in the sign at the same time, instantaneous. This is against, there's some magic here, right? How the planet Earth knows that at the same time something happened out there in the solar system. I mean, what is the spirit, the ghosts that are mediating that? I mean, our intuition is that physical forces or physical influences takes time to propagate. You understand? Change of forces at a given location immediately change of the configuration at a given location of the source of the forces, immediately change the forces at another location, and therefore change the acceleration of the particle at another location instantaneously.
And that's the problem with any kind of field, gravity field, electromagnetic field, whatever that's the concept of a field.
Newton mechanics, we're talking about a gravity, and it's true, and we talk about electrostatic, like the examples that I brought, they have similar form, and they also act instantaneously. Electromagnetism is a more modern notion of physics which Newton didn't have. And when we'll discuss next week electromagnetism in its modern version, we'll see that electromagnetism is correcting this deficiency. So Maxwell equations for electromagnetism will not have this pathology.
The pathology being the immediate action from a distance?
Will not have action from the distance.
Because this brings like serious questions about causality. Something happens exactly at the same time.
About what?
Causality. About causality.
No, causality, the notion of causality is not instantaneous. It's, A causes B in the future. So
that's exactly the problem. If you change the position of the sun and immediately the Earth changes its velocity, then what is causing what?
Right, absolutely. So in that sense, that's what I put it. I put it up front. When I compare the principle of causality to Newtonian mechanics, I'm saying that aspect of Newtonian mechanics, that the forces act instantaneously, violates our notion of causality in that regard. Absolutely. And as I said, Newton himself was very concerned about that a change of a force or the source of force, a change of the configuration of the source of force, immediately changed the force on the state of the system far away. That's something that is indeed against our intuition and against our and what we can do. Newtonian mechanics has this flaw, has this problem, absolutely. So that's what we will deal with that issue in the first part of the lecture tomorrow. And next week, we'll see how electromagnetism, Maxwell equation, which is a more modern theory of physics, or physical system, will not have that. Spooky action from distance. Okay? Okay, I hope that tomorrow, or I don't know, by Sunday, the latest, I hope even before, we will have a homework assignment for you to exercise and think about those questions. My lectures themselves should be in the Moodle. I don't know if the first lecture was already in the Moodle.
Yeah, it's there.
Okay, so with some delay, not instantaneously, with some delay, I'll put my lectures, also the second lecture in the Moodle. Okay, more questions. I want to give you, I just want to give you I was very explicit that some parts of my argument are maybe weak also. So don't worry if you don't agree with me, that's fine. You have to understand me, but you don't have to agree with me. That's the nature of what we're discussing in this course. You know, some of it is physics, and I insist on this is it, and some of it are the border between physics and philosophy, and there is no consensus about them, and you don't have to necessarily agree with my position. That's fine.
I have one question. So
yes.
I completely understand all the principles and everything. And I wonder what would happen if you have like more than one initial condition. Like now you gave the example of one initial condition. And can you comment something if you have like more than one? And then in that case, what would happen?
Well, you cannot have, in a system that I described, you cannot have two initial conditions.
Okay.
When I'm saying initial condition, I just want to explain. It's the initial positions and velocities of all the particles in the system. It's not initial condition of one particle. Then you can say what initial condition of the other one. No, it's initial condition of the entire system. Okay, so you have a closed system, maybe the entire universe, maybe some, I don't know, some box which has something moving inside it, or springs and balls and bouncing back and forth. All the particles, all the objects in the system, you have to specify their location and their velocity simultaneously at some time, which we call initial condition. So if this is the definition, you cannot have at the same time another initial condition. You cannot have that. You can, of course, say what happens if I were to have instead of initial condition A, to have an initial condition B. That's fine. That's what we discussed. How the initial condition changes that, selects a trajectory. But you cannot have on the same trajectory, you cannot have, I have two initial conditions. It doesn't mean it, okay? Initial condition is exhaustive. It's complete description of a state at one time. At that time, you cannot have two of them. Okay?
Yeah, that makes sense.
Good.
Thank you.
If you now say at time t equal to 0, I set initial condition. And now I want to determine initial condition at time t equals 1. Well, if it is along the trajectory, fine, you didn't do anything. If it is it's not on the trajectory, that you can only do by applying forces at time t equals 1. And that's exactly the kind of forces or perturbations that I described. But if you don't touch the system, then that's it. Okay? Good. More comments or questions? Okay, if not, then we'll see you. We'll see each other next week. Okay.